coming. It's a whole line of work, so I will not explain every single thing that we do, but I'll try to give you the most important ideas, especially in the first hour, and then we'll take a little break, and then I'll get into a little more technical stuff related to how we actually do the expansion estimates for Strassen. And you can see how the same ideas apply right away for Strassen-like algorithms and generally for recursive algorithms. And then how far you can take it is essentially up to you. So if you want to take that technique and use it in your work, then we would be absolutely delighted, of course. Okay, so the main papers in what I am going to explain today are perhaps those three. And they exist in, one of them exists in a conference version and a journal version. So if you want to see the short version, this is the SPA 12-page version. But if you want to read all the details, it's better to read them in the Journal of ACM. That's 20-something, 30, maybe even 30 pages. Okay. And if you're curious how these ideas apply, I will say a few words, but if you're curious about how these ideas apply to parallel stuff, then you should read this 2012 paper. And we have further papers. We also have papers on rectangular matrix multiplication and other things that kind of give you the same approach applied to these other situations. Okay, so what are we doing? We call it communication complexity of algorithms. Now, of course, everybody in this audience probably has heard communication so many times, but then it meant probably something else. Usually it means you have two or more agents and they communicate over a channel. And the purpose of that is really to communicate information, right? Versus in our approach, the purpose is communicate intermediate results along the computation that you are performing, okay? And so here is the story, and I'll come back to these pictures a few more times. We have an architecture. It could be sequential, that's a simple picture for that, or it could be parallel, that's again a very simple picture for that. And we work on a huge problem. So the number of, well, the amount of data, I should say, is so huge that we can never fit it into fast memory here or one processor memory there, okay? And so that's why we either have to do it by always going between slow memory and fast memory, or we have to do it by involving several processors and letting them split the work and communicate intermediate results to each other, okay? So once again, what is sequential and what is parallel? There's very, very simple models for that. So you see cache or fast memory, which we imagine to be limited. So there's a certain constant that limits the size of that. And we imagine that there is a slow memory, which is unlimited. So imagine this is infinity, size infinity. Of course, you can say, well, wait a second, reality is richer than that, right? You have a whole hierarchy of memories usually, and you have very fast, a little bit slower, and a little bit slower memory, and then something kind of virtually unlimited. But as a first approximation, we want to understand at least this model. And if we understand that, then we can also make some implications for, see some implications for hierarchical models, which is a little bit of a step, but it's not very, very hard. So we have a few remarks on how you can also consider the fully hierarchical model. Okay. Now what's parallel? Again, this is a simplified situation where we imagine every processor has the same memory size. So they're all kind of the same, okay? So all these guys, all these computing entities have the same local memory. And they can only compute stuff. The same applies here. When you perform operations, you can only perform them if all your operands are sitting in fast memory, right? And then likewise here, an individual processor can perform anything only when all its inputs, all its operands are sitting in its local memory, okay? And then as we are doing this, we transmit information using what's called a broadcast. And again, that's a simplified assumption. Reality could be more complicated than that. But in the simplified assumption, the broadcast occurs simultaneously to all other processors. So this guy, if he wants to say something to all the other guys, it's done at once, okay? And technically, well, this exists, okay? this ignores the topology of the network. Again, if you have a complicated topology, you don't want everybody to be sending stuff simultaneously to everybody else. Maybe you have some restrictions in your network. You can also take this into account. This, this further complicates matters. But again, as a first approximation, we want to know what happens here. Okay.
When you broadcast to everybody, it costs you, let's say you broadcast 1 bit, it costs you 1 bit of communication or the number of process of bits?
So we imagine it costs you just a unit of communication. Yeah. So maybe one main take-home message that I'd like you to retain from today is that in this admittedly sort of simple models, there is a single parameter that predicts how much you have to communicate no matter what, which is a rather striking thing. Yeah? And this parameter has to do with graph expansion. And what kind of graph expansion, what kind of parameter, I'll explain in all the subsequent slides. Okay, so once we understand that, so that's sort of the main idea here. Once you get the main idea and see how it applies, you can actually develop good algorithms based on this idea. So that's this practical upshot of what we do. And I should mention that I don't write code myself, but we work closely with people who do. And there are major results, practical results, where these ideas are implemented already, and then you can see actual speed-ups. So maybe I'll show a couple of graphs for that before we continue. So this is a graph that shows effective speed, right? Effective performance. So this little vertical axis is labeled by 2n cubed divided by p divided by time. Okay. Now let me explain. This is a parallel situation. So p is the number of processors or cores that you're using. And the scale for p is here. That's the x-axis. And it's not a linear scale. It's more like a logarithmic scale. So what you see here is roughly logarithmic. And what you see here, as I said, is the classical time, the time that you would spend on matrix multiplication if you do it in the most straightforward way. So that's why it's not the actual, amount of operations. But we pretend we need to have that many operations. So it's 2n cubed divided by the number of processors divided by actual time. And then what you see, you want this curve to be higher because you want to be very effective, right? The higher you are, the more effective you are. And so this is the graph for scale APAC performance for various number of processors. This is a graph which is already better for classical-based new algorithm improving over scale APAC. And then you start seeing Strassen and the performance of Strassen. So there is a Strassen-based parallel algorithm, which is from 1995. Okay? And then finally, here is the punchline. Here's our parallel algorithm of 2012, and we exceed the theoretical upper bound on anything classical related. Well, classical based. And we go to this red curve. Okay. Now, because we're dividing by p, these curves are roughly horizontal. They're not exactly horizontal. Of course, if you don't divide by p, then your curve will start growing with the number p. So to suppress that and to show it kind of proportioned correctly, right? I divide by p, and ideally we want to have almost a straight horizontal line, and if we're close to the straight horizontal line, we call it a perfect scaling across processors, or even perfect strong scaling if you really have a horizontal line. But again, reality is more complicated than that, so you don't get a straight line usually. But yeah, it's pretty close. So the scale APAC is almost a straight line, and then what we do deteriorates a little bit, but relative to all of this normalizations that are going on. Okay, here's another little graph. So here the number of processors is fixed, so there are 32 cores. It's a slightly different story, right? 32 cores are fixed, and what varies is, what is our picture? Yeah. Oh, yeah. The size of a matrix, and just like Yuval was telling us, there are 3 parameters, right, that describe matrix multiplication: the first index size, the second index size, the third index size. So this is the multiplication of what? 64 by k matrices, right, and k by 64 matrices, resulting in 64 by 64 matrices. And k, the middle parameter, will vary. So that's actually rectangular, right? So the k parameter varies like that. So you see very large values of k. And then you see actual performance of Intel's math kernel, which was, until recently, the best available kernel for this kind of stuff. And you see our algorithm, so that's maybe a more impressive graph to look at, because you see the speed up of 10 point something, and that's very manifest in this graph. Okay? And then finally, the most impressive little graph is this one, which shows that we are performing very, very close to machine peak. So this algorithm that is based on the work that I'm about to describe, again, benchmarked on certain things, right? So it's benchmarked on Hopper, which is a Cray machine, and it's running up in the Lawrence Berkeley labs. It's rectangular matrix multiplication. The sizes are fixed. Okay, so that's, again, you can say, well, that's a particular, very particular benchmark. But again, it shows what's going on. So scale APAC does certain things, and our algorithm goes much better, much faster, achieving almost the machine peak performance. So we are kind of taking the machine to the extreme. Okay, so that's a picture. And then there are many more graphs. So I will explain again what our model is. What graph expansion gives you, how it applies, why do graph expansion. And then I'll say a few words about this parallel stuff that comes out of that. And this is a little bit trickier, so I don't know how much I'll spend on this. But I want to go into this part in quite a bit of detail. So in the second half, I will explain in detail how you perform this graph expansion analysis. Okay. So maybe not this, but this. Okay, so here's a picture. And just to say a few more words about motivation, the total running time your machine will need consists of 3 parts. Okay? The first part is arithmetic count. So it's the number of flops, arithmetic operations you're performing, times the cost of the arithmetic operation. Let's say that all arithmetic operations have the same cost, right? So that's the proportionality factor in there. Then this is the number of words you have to send and receive as you communicate this stuff, right? Intermediate results. So here it means reads and writes into slow memory, right? And then here it means sending to others, right? And in this little model, you also actually have to package your words into messages when you broadcast. And there is a certain packaging cost, which is another constant times the number of messages you have to send. And for simplicity, which is actually essentially correct, for simplicity we can say, well, this is proportional to this, right? So we can forget about this extra piece, and we can say, well, there is a new proportionality factor times the number of words. And again, if your model is a little bit more difficult, you can also look into how exactly the cost of messages depends on the number of words sent. But that's a function, basically. This is a function of this. Okay. So why is communicating not the thing you would want to have, or you would want to do a lot during your computation? For this reason. These are 2 Moore's laws, one for improvement in hardware, in arithmetic, I should say, and the other for improvements in communication. So what you see is that the processor speeds and the hardware improvements there occur at roughly 59% a year rate. Okay, so it's a good rate, right? So every year, these speeds go up by 1.6, roughly, right? So 159 for 1.59 is your factor here. But these improvements occur at the rate 1.23. That is 23% a year, roughly. And then for parallel, so this is all, you can read about it. There are statistical results on that. There are reports issued every few years on these trends in hardware and so forth. And so you can see these numbers. These are fairly recent numbers. So here again, 59% a year improvements in processor speeds, 26% a year improvements in communication across. Okay? And so what you see, because these factors are quite different, and we already see that, the costs of communication has become much larger than the cost of doing arithmetic, and the gap is only increasing. So this is your bottleneck. These costs are larger than those costs, so you have to organize your computation so that you become communication optimal. You cannot fully avoid communication, but you want to be as minimal about it as possible.
So am I right in your answer to Avi that you're assuming that you're able to broadcast?
All at once, yes.
And isn't that not real? I mean, as the number of processors get really, really large, as they do in massive parallel processing, would that be not a good assumption that that you would be interested in not sending the same thing to everybody, but some kind of message passing or something? Some processors are talking to some processors.
So I imagine some people here know more than I do about exactly what happens, but this broadcast exists, right? So you can broadcast simultaneously to everybody. Well, it depends on what your connectivity is. Yeah.
He was in the millions. In some of your graphs, he was in the millions. Is it the use broadcast?
Well, I mean, if you're doing math, if you're doing like Google does or Amazon, they're not doing broadcast. They're doing sending certain things to certain processors.
Right, right.
But so this wouldn't address that. You don't really look at that.
This is right. This is a simpler model where we pretend we can do the broadcast simultaneously. If you have to incorporate further costs, then of course you can put the dependence there and see what happens, right? So it's going to be a more complicated estimate. Well, ours, if anything, is over optimistic, right? And so if we get lower bounds on ours, then these are going to be lower bounds on more complicated situations. And we are interested mostly in the lower bounds. So of course you're right that the reality will take this number of machines probably somehow into account, and there will be higher costs here. Correct. Yeah, but what I want to say, even with our simplistic approach, if we assume the simplistic approach and then create algorithms based on that, we still see great improvements in performance. Now, there are lots of issues like the exact scheduling of your parallel algorithm and stuff like that. And all of that has to be done, with respect to the architecture that you have. So you have to kind of think more about what you have, right? And then this is then a question of how exactly you're going to implement that. And as I said, this is hugely simplifying certain things. But even that approach with the simplified assumptions is new, and so that's what I want to say. Yeah?
Isn't some of the issue about broadcasting or not broadcasting also folded into your throwing your messages into the words, the kind of overhead for that sort of network communication?
So you can incorporate, right? You can incorporate these costs. Yeah, it's kind of there. Yeah. So if you're very curious about, this exact costs, how they will occur, right? And then all the different situations that will occur. This is too simple, but you can incorporate more complicated. Yeah, you can incorporate more complicated things. So I'm going to ignore this part. Okay, I'm going to ignore this part and pretend this is roughly like a new constant times the number of words. But again, if you're interested in more complicated situations, then you can put those costs there. Okay, so if we avoid communication, avoid is a bad word perhaps, we cannot avoid communication, and when we derive lower bounds, we show how much we have to do, right, regardless. So avoiding is a little funny, but maybe optimizing or minimizing communication is the right word. So if we minimize communication, we will actually have the greatest impact in terms of saving time, and the greatest impact in terms of saving energy. I hope I convinced you that regardless of how complicated the actual machines are or networks are, minimizing communication is a good thing. Do we agree on that? Let's hope so. Okay. So here's a very, very simple little example. Where you just do things the way we were taught in, in our first linear algebra class. And just for this little example, I want to kind of mentally compute communication costs. So we have a matrix A, we have a matrix B, and we are going to compute things by the linear algebra 101 formula. Okay? So we initialize our little value Cij to 0, and then we keep adding the products of Aik and Bkj. So we need these two operands, Aik and Bkj, once we need to add stuff, right? And so we have to grab them. Let's talk sequential, okay? So we can grab them from slow memory, right? These are two reads from slow memory. We compute the multiplication in fast memory. We add it to the current count here, right? So and this updates the value of Cij. So okay, so if we do it, this is sort of the simplest possible thing to do and the most inefficient, presumably, right? So if we do it like that, how much communication do we have to perform in terms of the number of words read from slow memory? Well, there are n squared entries in C. We're doing square multiplication, so there are n squared matrix entries in C. And for each one of them, we have to do this. Okay? So how much do we have to communicate, read and write? Yeah. Yeah, so it's n cubed, right? So the costs are theta of n cubed. Do I need to explain theta? I had to explain theta in Princeton. So okay, big O. Do I need to write this down? No. Okay, you guys all know. So big O is an upper bound up to a constant, right? Big omega is a lower bound with another constant coming from below, right? And theta is an upper and lower bound. I mean, the point is that this is roughly n cubed.
What do we assume about the relative size of memory of fast and slow? How many can you store?
Here, so here I never said, here we are doing the stupidest possible thing. We always grab,
I understand. So
yeah.
we have
Oh, in general.
computation. So
Yeah.
it depends.
Yes, yes,
Whatever
absolutely.
depends on the
Absolutely.
size.
This is the size of our...
M has what, how do you think of it relative to
Well,
N?
capital M is fairly large, right? But then we want to work on larger and larger problems. So this guy can go to infinity, right? N is unlimited, whereas M is a certain constant. M is a parameter of your processor, right? It could be fairly big, but it's fixed. So we're not playing with M. We cannot change M, right? So M is fixed. You bought your processor, a year before. So that's what you have here. You're not enlarging M. So M is a constant. N is your data size in terms of matrices. It would be probably the linear size, right, going across. And this can be huge. So even though N is small, it's much bigger than M, which is big.
You assume it holds some numbers, right?
Yes.
The word size.
No, M is the number of words you can fit in fast memory.
Word is an entry of the matrix.
Yeah, a word is an entry of the matrix, right? Yeah. So I'm not going into what entries you have, how you represent them, all of this stuff. So yeah, that's the number of data entries that you can have. Correct. Okay. So now let's just do a little variation on that. We have this M, which is our memory size, remember. Okay, now, of course, what we did before was not the greatest thing to do. So let's just do it slightly better. What if we run the same thing blockwise? Okay, so what can we do? Well, in order to compute a little matrix multiplication entirely within our fast memory, we can accommodate matrices, and let's imagine we are splitting into little square blocks. Okay, if we're splitting into little square blocks, then these blocks have to be of size roughly square root of m by square root of m. Or to be very, very precise, you can say it's square root of m over 3 times square root of m over 3 to put a little block from A, right, a little block from B, and compute the product, which is a little block in C. Okay? So these are the sizes. Okay, so we have how many of these blocks? Well, we have n over square root of m quantity squared blocks like that. I'm ignoring constants, all right? So n over square root of m quantity squared blocks like that. For each block, we're playing the same game, right? We're playing exactly the same game. Now, these guys are blocks, right? So we need initialize our little block to 0, and then we grab a little block from A, a little block from B, multiply this in fast memory, and then add this intermediate block value, right, to the current block value Cij. And so what is going to be the communication? Well, it's going to be that quantity now, right, cubed, and in each block we have order m words or elements, right, square root of m times square root of m. So this is the cost that's going to be incurred, right? So we're incurring this cost. So this is n cubed divided by square root of m. Okay. And this is already definitely better because, you know, this could be a big improvement if m is big. Okay. And this was pointed out by various people in various papers. So Cannon had a thesis in 1969, and he chose m. Now, okay, here is your question again. Can m depend on n? Well, you can pretend that you can choose m, all right? Or maybe your matrix size is particularly good. So Cannon considered this situation where m was theta of n squared over p, where he looked at the parallel situation. And he got kind of this bound, right, but with this choice. This is for parallel, right? And then there were other works by McCall and Tiskin, and then later Jim Demmel and Solomonic, 2011. So they did it for any m. So it extends to the parallel case as well. And then you'll see this improvement due to the parameter p. Okay. And the question again, can we do better than that? Okay. You can say, well, that's a variation of what we saw before, which was a very simple algorithm. Now it's a little bit more sophisticated where you do it blockwise. Can you actually do better than that? And what we showed in the first paper that was on the first slide was that actually the answer is no if you are restricted to operations of the kind that we saw. That is, this Cij is computed using the classical matrix multiplication formula. Meaning what? You can do these computations in various ways, but you're not allowed to use distributivity of your operations, okay? In other words, maybe you grab these blocks or do something, at various points of time. Nobody says how, but you have to do it according to the formula. So the eventual result will be performed according to the formula. And so that's a lengthy paper, and to explain what's going on, we actually track down the indices that are being used, and we employ a geometric argument for those indices. And so basically, it boils down to where these indices come from, and then we look at the geometric representation of those sort of as a 3D lattice body, geometric body, and then look at their 2D projections, which would be these pairs of indices. And then we argue about that. I'll show a little diagram. Maybe let me skip. So they did it actually for sequential math. Yeah. They did it, and oh yeah, and I can show a little bit of what went on there. What we did, we extended it to all sorts of other things. We extended it to LU and Koleski and lots of other algorithms, showing that if you're using the same approach, that's so. Let me just skip. Maybe I'll get to this just a second. Let me show you the geometric picture there. if I may.
But what exactly is the model?
Yeah,
under
yeah,
which
yeah.
are
So
proving
that's,
the lower bound?
yeah, that's what I will explain. Just a second. Here we go. Does anyone remember how to come back to the page that view? Enter full screen. Let's try this. Nothing shows up. I think we had this problem before. Well, I see it on my screen, and I see it here, but I don't see it on this screen. That's too bad. Sorry about that. The picture there is a fairly familiar picture. Just don't want to redraw it on the board because it will take me a while. No, 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 let's wait. So hopefully.
So what is the model under which you prove the lower bound?
So the model there is that your computation, thank you. So I did unplug it and plugged it back, but it didn't come back. Uh-huh. So you changed the resolution?
Yeah. I
Okay.
just scaled it down to something small.
Okay, yeah. So, yeah, that's this approach. And so what we imagine is, well, so, okay, this is the form, right? So we imagine in general that our entries that we will compute, so these are some elements indexed by, you know, a certain index set, will depend on input elements where you have, again, 3 index sets. So here you have, you know, the index set for I, K, and J. And so K runs over the index set there. And these are entries we will have to get from slow memory, okay? Plus, potentially, we have to compute other things. But, you know, these are the products that we will be computing. That's our assumption, right? And then in general, you can replace products by any binary operations you want, right? But the point is that to actually compute them, you need to get those at some point from slow memory to fast memory. Okay, and that's the picture in 3D. So it has to do with this 3D volume estimates, where you are given sort of this volume as a function of the areas of the projections on the xy, yz, and xz plane, or rather, I should say, jk, ki, and ij planes, right? And then your geometric body can be much more complicated. So it's some crazy geometric body. It's not a nice little box like that, okay? So it would be a nice box sometimes, but not usually. And so it could be a crazy geometric body, and there is a result from late 40s, I think, yes, 1949, by Loomis and Whitney that shows that regardless of how crazy the geometric body is, the volume is bounded by the square root of the product of all the three areas. And this, by the way, generalizes to high dimensions, okay? So if you have a more complicated computation to perform, but your assumptions are, again, that you need all operands grabbed at some point to perform your operation, so formulas like that, potentially plus other functions you are computing somehow, without these inputs, that's perfectly okay. I don't know, you can add, if you need to add other things that do not depend on those entries, that's okay too. But the point is that there will be these volumes estimates, and then the volume here, of course, we have lattice bodies, as you said. These are lattice bodies, so volumes have to do with the number of points, integer points sitting inside, and this is the number of elements that we will be dealing with within this computation. Okay, so this gives you, so for this, we can see that if we have O of m inputs and outputs, then we can perform big O of m to the 3/2 flops, okay? And we will have to do that much communication. This is the complexity, the communication complexity per flop. And then this gives you this bandwidth, which is the number of words, data words, to send and receive, which is going to be omega of n cubed divided by m to the 1/2. So that's exactly what went on before. Okay. But now Strassen and Strassen-like stuff is completely different. I'll just get back there and then we'll take a break, okay? Is that okay? So I'll just indicate what happens there. Here's Strassen. And how do I get to... Uh-huh. This? But it will start it again, right?
It should start
From this slide? No, it doesn't. That's why I was asking. I want to start here.
Okay.
Sorry about that.
That's no problem.
Oh, play from current. Oh, there was this play from current, yes. Fantastic, thank you. Yeah, see, live and learn. Yeah, so when we have Strassen, there will be a difference, and then we'll just say what happens differently. Before we start, so we don't actually grab those elements the way they are, we first combine them, and then we multiply them in different ways, because we will be using distributivity or multiplication. And by doing that, we can actually dramatically reduce communication, not just the arithmetic, but also communication. So, should I stop now? Is that a good point? Oh, we started at 10:30, so maybe I'll say a few more things, right? And then we can draw. We can stop maybe in 20 minutes, and then I'll get into more technicalities and Strassen. So, okay, so let me explain just what Strassen did. And again, probably this audience doesn't need an explanation. We have seen this already many times. So a quick recap. You split your matrices right into 2x2 blocks. And then you note, which is the gist of that Strassen method. So that's his great observation, that you can combine these blocks first in a certain way, right? So you're combining them first and then multiplying next, using 7 multiplications that will be block multiplications. And by doing so, then you can kind of unscramble those results, and then you get those 4 blocks back. So that does not adhere to the paradigm from before, because we are not multiplying what we had to multiply according to the formula, right? These are different things. We first combine things, so we compute these intermediate results, and then we do 7 multiplications, then we unscramble those 7 multiplications linearly, but that does not adhere. If you try to make it into the form before, you will not, okay? So that's a big advantage. And if you run this recursively, then you'll see this 7 number of multiplications translates into this magic exponent that Strassen obtained. And the total arithmetic costs become theta of n to the log base 2 of 7. Of course, if you make 8 multiplications rather than 7, it will be n to the log base 2 of 8, right? Which is 3, which is familiar, right? But that's the big improvement. So, all right, so once you notice that, then were all these great advantages achieved based on his method, his ideas, further improvements to these algorithms. So that's just an incomplete, perhaps, list. And then there are newer things, as we learned recently. But, you know, I just stopped here. Okay, so that's the current complexity bound in terms of arithmetic complexity. And these are Strassen-like methods. Except for Kohn, Klenberg, Segedy, and Humans, this is a group theoretic approach. But so far, they were only able to emulate what was done using Strassen-like approach. But they were not, as far as I know at least, you know, they were not able to achieve improvements over what was known. Okay. Now, that's complicated, and this is not implemented, but technically, you know, it's a method that exists. So this was a record. Coppersmith and Vinograd was a record for many, many years until recently. And we learned about that the other week. OK, so here is the deal with Strassen and Strassen-like. So remember our great bounds. These are classical bounds, right? If you do things classically, that's what you have to do, as we found out. So this is n over square root of m to the power log base 2 of 8, OK, times m, the same here, divided by p. Now, for Strassen, not surprisingly, this exponent becomes the Strassen exponent, which is log base 2 of 7. Okay, log base 2 of 7. And if you want to now look at Strassen-like, then whatever exponent you can produce, so if Run comes up with exponent which is, you know, 0.1 better than the current bound, and then we can put it there and get the bounds on lower bounds in communication. And if Yuval finds an even better one, then, you know, we can put that there. So, fine. Or everybody else in the audience gets another bound, you know. This will be there. Whatever bound you give us, right, so you give us a new magic exponent, we can use it to give you a bound on communication. That's the beauty of it, okay? So how does this go? And here is the main idea. So,
You're proving a low bound.
yeah, that's the important thing.
You're proving a low bound given a better algorithm. So there's a better exponent that one just discovered. I doubt very much it's working on it, but there's a better algorithm, and now you're saying I'm proving
Yeah. So for that, if you give me a better algorithm, we can give you a lower bound on its communication. Yeah.
But the dependency improvement, the heuristic improvement, so we can use the matching upper bound.
Well, so it's actually gonna be, so this is analysis of an algorithm, okay? So we'll tell you, if your algorithm satisfies certain things, then we can give you a lower bound in its communication. Given its lower bound, we can suggest to you how to actually run this algorithm so that you will get a matching upper bound. So you can run it so that you will be actually doing it in the communication optimal way. Okay? And by an algorithm, I mean this. So this is the directed acyclic graph which describes your algorithm. And you know, here comes a little nuance, which I will get to in a second. So these are, let's say, your input vertices. So they will tell you, you know, we have, I don't know, 3 by 3 matrix and another 3 by 3 matrix. We have actually 18 input values, right? So 9 times 2. And so all of them will be sitting somewhere as We can imagine these vertices we started from, right? Then they get combined in some binary fashion. This could be a plus, it could be a minus, it could be multiplication, right? Whatever. So we combine them and then keep going. And so these are black vertices are intermediate values. So we keep combining. This is a directed graph because we proceed from inputs, right, through all the intermediate stuff until we reach outputs. And so in this toy graph, which has nothing to do with matrix multiplication per se, we've got, what, 5 inputs and 2 outputs and a bunch of intermediate black vertices. Okay, so it's a very little graph. Actual graphs that tell you what an algorithm does are much, much, much bigger. Okay? Now, if you're running it in parallel, then effectively you're assigning various vertices to various processors, right? And so that's the game that you will be playing, and this has to do with scheduling. So you want to say, well, actually, this operation will be performed by processor 1. Okay, for that, these inputs will have to sit in processor 1's fast memory, well, local memory. Okay, so this is the game that you will be playing. If after doing this, you decide that the next operation is going to be performed by processor 2, then you will need to actually, well, broadcast. If you don't like broadcast, send directly from processor 1 to processor 2. But in our model, broadcast, right, to get this result, this intermediate value, to the next processor. Okay.
But if you're in the sequential case, this is just a pebbling game.
In the sequential case, correct, this is the pebbling game. So what you do is you have to decide, you have your local memory. You cannot fit everything into local memory, right? So again, when you're performing this computation, the inputs have to sit in fast memory. And so, right, before we pebble those vertices, we cannot go ahead and pebble this, right, and perform this. So this is correct. But the pebbling process, per se, has to do with the implementation, how exactly you're running it. Correct.
So it's a fixed computation graph. It's always a fixed algorithm.
It's a fixed computation graph. Yeah.
So you need to analyze every...
Yeah. So our approach is approach to algorithms, right? It's not an approach to a problem. So this is its biggest deficiency. We wish we could say, okay, given a problem in any kind of combination graph that describes this problem, we can say something, right? But that is tricky. But we can analyze graphs and classes of graphs. That's correct. Yeah.
Question. So everything's broadcast. So it's not like you're worried. So it could be that all the nodes know everything that all the other nodes know. Something like this.
Well, this will cost you. Yeah.
Right. Their memory is limited, but
It can never happen at any moment of time that they just have all input values available.
I mean, I guess originally everybody has some entry. Say the entry is in one place, different places.
Well, the original, this is already communicating stuff, right? So to get the inputs into local memories of certain processes.
It's announced to everybody. So how do you know there's not some way to sort of combine the announcements?
Well, your processor has to grab, so it has to grab something that is coming and place it into its local memory.
Right, but it's all everybody's stuff is.
So you see,
I mean, that node could be grabbing things from anywhere, right?
technically yes,
Right.
but this will cost you.
But
If it's not already in your processor's memory, to get it there will cost you a unit of.
but not more than for your broadcast is free. So if I send something to you, actually he could grab it for free because it cost me 1 unit broadcast.
But it will still cost. It will still have a cost.
It doesn't cost any more than him to get it.
It will still have a cost, right? So
If I paid $1 to send it to you, that 1 unit pays for broadcast, so you can to everybody, right?
technically, you can send it to several processors at once. If they all need that operand in their local memory, they can have it in the local memory. But the point is, yeah.
Right. I know, but I'm just wondering if there's any kind of coding or any kind of way to combine information so that it's not, I mean, looking at it as a graph like this,
Yeah, your constraints come from the fact that
I can't hold too much.
Yeah, you cannot hold infinite amounts of information. Right, right. That's the most important constraint that you have. So it's not like by being greedy, you know, you could. Yeah. You cannot combine information in magical ways. That's right. Okay.
Oh, you're saying the other.
Broadcast corresponding cannot, so theoretically, you could have, you're not charging for the edges in this graph, you're charging for the number of operations, which is the number of vertices.
Yeah, it's a cost in terms of vertex numbers.
Right.
Correct.
So
Yes.
require the fan in to each vertex is 2, right? Because an individual operation is
It's always binary.
It's always binary.
Yes.
So you can fan out as much as you want. That corresponds to a free broadcast.
Right,
So
correct.
The cost of operations is captured by the cost in terms of vertices.
Right. That's correct. Yes. Exactly. So you know, I think we are very focused on broadcast issues right now. Let me go back to simpler things. Just sequential case, right? So you're reading and writing into slow memory. So this could be your reads that you have to perform, and this could be your writes. Now I'm actually, so if this is, it's like you focus on a certain segment of computation, and this can correspond to locality in time. So these are the operations performed one after the other, for example, right? Oh yeah, by the way, time, if you want to begin very precise, you can say, well, this graph is kind of partially ordered because it's a directed graph, right? You now have to totally order it by time because you're doing stuff in a certain order. This total order has to respect the partial order that you have. This is the pebbling condition, right? Again, so you have to respect the partial order. But other than that, it could be any total order. So our analysis works for any total order, any implementation that you can think of which respects the partial order on this graph. Okay, and then here comes the idea. So let's look at a little segment of computation which is performed, let's say, you know, these are the operations performed, you know, within a certain segment of time. I don't know, 5 seconds or 5 milliseconds of time. Okay, and so what is happening here, these are sort of this pseudo reads operation. I'll explain why pseudo. These are the pseudo reads and these are the pseudo writes operations. Okay, now why? Because, and again, the focus is on vertices actually rather than on edges. In order to start the computation of the segment, well, so these are the first two operations in this partial order. Well, you have to have all inputs for those, right? So you have to grab them. They may be sitting already in your fast memory. This can be the case, right? If not, you have to grab them from slow memory. We agree on that, right? So this is sort of the pseudo reads because it doesn't tell you whether you're actually reading them, right? But these are candidates for reading, okay? And then likewise at the end, so this is the last ones, then you exit your segment, okay? That means that maybe you will write them into slow memory, I don't know, or maybe you don't need to write them into slow memory because the next guys can just take over, right? And then maybe these are results staying in your fast memory, great, and then you continue next, okay? But now let's see what this approach actually gives. So this is a little suggestion already why graph expansion is interesting because you can see that, you know, if you start splitting your big graph into small chunks and then arguing about these chunks, you start of kind of getting the gist of reads and writes. So we want to estimate the number of vertices Rs and the number of vertices Ws. What happens if we get these numbers? Well, then we can say the actual number of reads is at least what? Rs minus M. Yeah? And the actual number of writes we have to perform is at least Ws minus M. Yeah? Because again, your local memory or fast memory is not infinite. It can only hold M entries. So if this is bigger than M, then you have to read at least Rs minus M, right? And then likewise, if this is bigger than M, you have to write afterwards at least Ws minus M. And that's, you know, it's such a simple idea, but that's what gives you this balance. Okay.
So this kind of expansion arguments are used in pebbling lower bounds. So what's the difference?
So what do you call pebbling lower bounds?
You want time space trade-offs. You want to say
Yes.
if you have n memory, then the number, the total number
Mhm.
F may have to be much bigger, right? To actually make this multiplication and
Mhm.
variety of other.
So we use small set expansion bounds. Are they the same as what you call? I mean, I just.
These don't use small set. They use standard.
Yeah, but I'll show you why we use small set expansion to get this bounds on RS and WS. Okay, so what's expansion? Again, everybody here probably knows. That's the general expansion parameter, right, for a graph. So you imagine you split your graph into a subgraph. So a subset of vertices and everything else. So just a cut. Then you count the number of the number of edges going across. And then you divide this number by the number of edges restricted to this part.
So you consider a darker graph on the line?
Yeah, so I'll explain. That's the general expansion constant. This is the same as the Cheeger constant. I think that's exactly the same, right? And it has to do with undirected graphs, and it has to do with splitting graphs into two chunks, where the sizes of those chunks are unrestricted. Well, of course, you have, if you split into two, one of them holds at least half of the vertices and the other at most half of the vertices. But, other than that, it's unrestricted. Okay, and there are basic important results on that. Again, everybody here probably has seen many, many talks. So basically, this expansion constant is determined by the spectral gap of the adjacency matrix that you can write for an undirected graph. It's a symmetric matrix, so all eigenvalues are real. And for simplicity, if we normalize the leading one to be 1, then the spectral gap will be given by this difference between 1 and either the next one or the very last one taken with absolute value. Yeah. So this is this great result, very well known here due to all these people, that shows a lower bound and an upper bound in terms of the spectral gap. That's a classical graph expansion. Now, we don't want to do this quite yet. We want to do small set expansion. And now, what does that mean? That means we restrict the size of our graph that we single out, the subgraph, the subset of vertices that we single out, but then we will play the same game. And for our approach, we can actually develop, we can use these ideas, the spectral gap ideas, to estimate the small set expansion, or we can just directly estimate this combinatorially. And this will be in the second half. But the point is, so that small set expansion values will determine communication complexity of our graphs. And I will just get to one, so I'll explain the idea and I'll stop. Let me get to this. This is Strassen, Strassen, Strassen. We don't need this. Here's what I want to explain, okay, and then I'll stop here, and then we'll go back and look carefully. So think sequential for now. Okay. Think sequential and think about your algorithm being already scheduled. Okay, so that's the actual run of the algorithm. And we go and then look into segments of this, where segments will be determined by your arithmetic complexity. So if somebody gives me a nice omega, I'll take it, I'll divide it by 2, and I will take segments of size theta, so of order m to the omega over 2. Okay. And when I look at the segments, that's the hard part. I will need to show that every one of the segments will have at least 3 m vertices with incoming and outgoing edges. So again, not counting edges per se, but counting vertices with incoming, outgoing edges. Okay. And since we have already made this observation that then you subtract 2m, right? We subtract m and we subtract m again. That means we will have to perform at least m reads and writes. So this is the complicated part. I mean, it looks very easy as a general idea, but that's the part where you have to do work. Okay. And so for these segments of this size, you will have to do at least m reads and writes. Once you establish that, the rest is a piece of cake. because the rest just says, okay, what's the total communication? Hey, the total communication is also the number of words sent and received, right, or read and written, is the number of such per segment times the number of segments, okay? Now, per segment, we know we're doing m, order m operations, so that's that. And how many segments do we have? How many vertices do we have in our graph, in our computation graph? Yeah, n to the omega, correct. Well, plus inputs and outputs, but this is less than n to the omega, correct. So actually, the arithmetic complexity is the size of the graph, well, the vertex size of the graph, correct? So that's what happens here. We have n to the omega divided by these block sizes, segment sizes, okay? So this is the entity that will occur here times this theta of omega. Oh, sorry. Omega of m, or theta of m, to be precise, right? And then you combine all of this, and then you get a lower bound. So the lower bound will be n to the omega divided by m to the omega over 2 minus 1. So that's the main idea. And then this is hard. So this needs proofs. And for Strassen, I'll just walk you briefly through the proof. But maybe we'll stop here. I mean, they are related, of course, but they become different arguments. They're not the same argument at all. So here's Strassen. And let's just revisit what Strassen does. This is the actual computation graph of Strassen, right, for what matrix is 2 by 2. So it's like in excruciating detail. You can see what's going on. So these are the entries of A, labeled 1, 1 through 2, 2. These are your input values. Unfortunately, not blue. The output will be blue. So sorry about that little discrepancy. Okay, these are the entries of A. These are the entries of B. Then they get combined in funny ways. Now, let's just look at that. So they get combined to produce 7 intermediates, right? There are 7 intermediates. Why 7? Because we will be using these guys to multiply, right? Now, what about these weird things? What are the weird things? You do nothing, right? So actually, there is no operation that takes place because this just redirects you, right? So, I mean, if you read it like what you need here, you will need to grab all the way, the element all the way down there, which is your A22. And then likewise, for one of these products, you will need to grab, so if you're kind of reversing your path, right, so you need to go all the way back, right, and you're grabbing A11. So actually no operation takes place there, but it's lovely to have it drawn like that because it shows you those 7 intermediates, otherwise it's not very nice looking, okay? But this is very uniform looking, and it shows you exactly what this little graph is. We call this graph the encoding of A. And this is just one level of encoding, right? Because this is the actual 2 by 2 computation. So in fact, you just do it once, right? So these are your 7 intermediates. By the way, you can pretend that that's a unary operation that you performed, if you want, and this is not dramatically changing anything. It's up to you, right? Or you can actually be honest and say there was no operation to be performed, whichever you prefer. Okay, so this is the encoding of A. Now, the fun thing is that the encoding of B is the same graph. Yeah? It's described by exactly the same graph. Look at the operations, right? It's exactly the same operations, and that's exactly the same graph. Now, for our purposes, the actual operations, what happens here, whether it's plus, minus, is unimportant, in fact, right? It's a certain binary operation, but even in terms of operations, it's the same. Okay? So it's exactly the same. Then we got this 7 intermediates and this 7 intermediates, and there is multiplication performed exactly once, right? So they get multiplied exactly once. And these are these red dots, which are the multiplication dots, right? So there are 7 multiplications, and you grab the first from here and the first from there, right? The second from here and the second from there, and then so forth, right? The third from here, the third. And so it's a nice regular kind of picture. So you combine them in that order. And these are your 7 intermediate results here. And then you need to recombine them to kind of decode what you got, right? So there's a 7, you need 4, and that's the graph that provides this decoding. And it gives you, as a result, this C11 through C22. Now look, by the way, at this graph. This is almost like this graph. This is more of an accident, so you shouldn't assume that the structure of all these graphs is so beautiful and uniform, right? So it's all these are the same graph. But it's suspiciously close to actually what happens here, just because of the beauty of the method. Okay. Now, this is one level, right? So this is a 2x2 computation graph. That's a full computation graph. Now, what happens if you transition from, let's say, just transition from one level to 2 levels? Okay. So how is the situation going to change? Well, we had entries before, right? And now, if you're transitioning from one level to 2 levels, these are not entries anymore. These are what? These are little blocks, right? These are 2x2 blocks themselves. So actually, what happens here will look like this, right? So you kind of start seeing quadruple. Instead of 1 dot, you will see 4, right? This is your little block. This is the 1-1 block, right? This is the 1-2 block. This is the 2-1 block. This is the 2-2 block. And then what happens to blocks? The same stuff, right? So blocks get kind of, transferred around. So you get this block added to this block. The result is a new block. Then what happens here? So here you can't just go across, right? So what happens now? Yeah, then you have to do it recursively, right? So it's getting difficult to draw, right? But that's what you're going to do. So now this little 4 are going to be unscrambled, right? Well, or scrambled, scrambled here, right? So you get 4. You actually kind of identify them with the little 4 line from before, right? So this is the encoding graph that you'll have to insert in there. And then from those 4, you'll produce 7, right? And then from, let's say, those 4, you will produce 7. So you get those 7 intermediates, 7 intermediates. This is your layer of multiplication. Multiplication, again, occurs only once, no matter what you do, right? So you do a lot of linear stuff, right? So imagine now in general, there are several layers. How many? Log n layers, right? So this is your recursive structure, so you go like that, right? So, and every time the scrambling is linear because you just add and subtract, and sometimes just transfer exactly the same entry, right? And this is your linear scrambling that's going on. Then you finally get to all these intermediate values. You can count now how many you will have, right? Because what you were doing here, you were transitioning. So here, this is the transition from 4 to 7, right? And then you can see what went on before. So you can even count how many you will have, right? And then there is this one huge flat level of multiplication. You will do that. So that's what happens here. But imagine you will do this for every one of those little blocks, right? So keep going like this. And then you will start decoding. And then you go 7 to 4. That's your decoding. And then you have to keep doing the decoding according to. So this is kind of going back up this recursion. And then you end up with the decoded version. Now, so here are 2 things that I maybe said before, but I'll say them again. Notice that when we analyze expansion properties of this graph, we forget now about directions. We couldn't care less about directions at this point because we always look at reads or writes, right? Or, this sent and received. So we actually don't care how the arrows go. Once we understand what the graph looks like, we can forget about directionality, and we can say, okay, if we want to do expansion for, if we want to understand expansion of a certain subgraph, then we actually don't care whether the arrows in question go up or down, and because we will combine them anyhow. Yeah? So that means that we can forget about directionality. That's the first little point. And I wanted to say something else, which I already forgot, but maybe I'll get to this. There is another point. Oh yeah, here's the other point. I now remember. The other point is actually very important. We are interested in lower bounds. Yeah? So if we can analyze just the top half of this picture and get bounds on communication there, right, then this will produce a lower bound on the whole thing. So,
The top part or the middle part?
well, we can grab anything we want, right? So if we get a lower bound on communication, that just has to be done. Let's
Doing it on the bilinear when the multiplication part.
correct,
Yeah.
yeah, correct. So you can actually go and do it here if you want, right? Or you can go do it here, which is the same picture exactly, right? Or you can go do it there. And for all practical purposes, this becomes the easiest thing to analyze. So actually, our analysis applies to what we call the decoding part. Okay? The decoding part is nice. Why is the decoding part nice, for example? Because vertices there have bounded degrees. Now think about that. This is a fact that needs thinking. I'm not proving this on the board. But the decoding part is nice in that you cannot get vertices of degree, let's say, log n. Versus here, you will. The encoding part gives you vertices of degree, which is roughly log n, and n is unlimited, so then you have to worry about this. Now, these vertices are nice and all have bounded degree. So we can even pretend this is a regular graph because we can put extra loops and make it exactly regular. And then there are all these results on regular graphs we can use, if we are keen on that. Or we can do it just combinatorially and not create these extra little things. But it's up to you. The point is that these vertices have bounded degree, which is very good. Yeah.
Why the encoding part have unbounded degree?
Well, we have to see what's going on, right? So how many times is something used, right? Look at this. How many times is something used? There are up to log n uses of a certain input value. You see?
I mean, what shows here on the slide is bounded degree, and they don't. And if you replace the 4x4 block, I mean 2x2 block, with I don't know n by n blocks, I don't see why should the degree change.
Well, let's see. So if you're participating, right? So there are log n levels, right? So you keep doing, let's say, additions of blocks. For as long as you're sitting in the block, this is one use, right? So for log n levels, that particular entry was used every time to, let's say, add to another entry. So you see, so it keeps getting used. It will be used up to log n times.
I mean, it seems that every entry will be added only to 3 or 4 other entries. Sorry, that's just the one.
Is it because of the zeroing part where you don't need to do anything?
Oh,
You will have to keep grabbing them all the time.
oh, my mistake. Because
So there
I
will
think
be,
the encoding
yeah.
part, you don't mean just the one on the bottom, but also
No. The encoding is all the way, right? And so there are
And
this,
also there are-
including this, yeah.
I mean, including the small one in
The
blue.
degree of the vertices.
Yeah, the encoding part is all the way to here. Yeah. So however many levels you have,
Oh, I
right? So you can just draw it on a little piece of paper and see that if you increase the number of levels, then there will be some operands, some vertices that will have degree log n.
Okay,
And that's not what we want. I mean, potentially we can also incorporate and look at them and do something about them, but we found that to be a technical slight obstacle. And so here we don't have this obstacle.
But when you do the algorithm,
Mm-hmm.
then you always have to do the encoding for it.
Again, but you see, we are only shooting for lower bounds. If we establish that just by doing stuff here, we have to communicate that much, right?
The lower one is going to guide you on how to do the operation.
Yeah, so the magic is, I mean, actually, we suspect that there is a nice analysis you can just run also here. It's just slightly more technically complicated.
No, what you run is asking. You promised two things. A, to prove a lower bound. B, that this
Right.
lower bound will
Right.
guide an algorithm designer
Yeah.
to achieve, to meet the
So-
lower
so-
bound with an upper bound.
Correct. So
For
what?
this you would have to know also what to
Yeah.
do
So
with it.
what we did was a little nonlinear. So we got these lower bounds. They gave us these nice bounds. So then, just looking at the recursive structure, we designed an algorithm that respects the recursive structure. And then provably for that, we could show that the upper bound and the lower bounds matched up to constants. And so the intuition came from the analysis there. We strongly suspect that you can run the same kind of analysis there. It's just that, you know, it needs a little more technical work. So we were, you know, since we always go for the easier, you know, argument if possible, we did it for this part. But I'm absolutely sure you can do the same thing here. It's just that, you know, that technical slight complication occurs, okay? And to circumvent that, we just said, okay, let's not worry about this part. Let's just do it for this part. So it's not, again, so it's not a regular graph, and it's not even a bounded degree graph in general. But then if we transition to this top, then the decoding part, then it will be nice, okay? So as I said, what does decoding actually do? Well, we have an inductive now construction. You have whatever, let's say you have n levels, and you want to consider what happens if you increase the number of levels by 1, or k. N is the size of your matrix, so let's not use this. But let's say you have k levels, and think of k as your log n eventually, right? And then you increase it by 1. So what happens is that you had the previous decoding graph at the previous level. Here I say decoding sub I, okay? You want to construct decoding sub I plus 1, so you grow it by 1 level. That means that you have to duplicate. Well, duplicate is a bad word. You have to have 4 copies made, right? So you have 4 copies made of what you already did. And then you have to assemble them using, well, however you draw it is a little bit tricky. You have to show that these are now assembled and mixed together using a copy of this elementary Strassen graph. So this is the elementary decoding graph that is sitting right there. So it's 4 to 7 connector graph. Yeah? So these are your pictures. So that's how you recursively do this. And then you can do things combinatorially, as I said. You can also do it even spectrally. What you will see is that, let me get to the most important point. You can see that the small set expansion parameter of the decoding, and generally let me put k here now, decoding sub k with k levels will be given by omega of 4/7. These are this 4 to 7 ratio numbers, right, to the power k. So in general, if you have k levels, you'll get 4/7 to the power k. Okay? So this is a small set expansion for graphs of this decoding nature. Okay? And from there, you can get, therefore,
What is the small, what do you use small? Not the first line.
this is not necessarily small. Now comes the small. Now comes the small. So if you have square root of m by square root of m matrices, right? So the size of your decoding graph is going to be what? Log of the square root of m, right? So k is a order log square root of m. And now we plug that in. So, right, this you establish in general, and then you specialize to the small part. This is inductive, and it takes 4 pages to do. So do you want me to?
What are the worst case sets?
So what you want to do, let's go back for a sec. So you want to see how your segment vertices are distributed. So because it's a recursion, maybe they are spread all over the place, right? So you want to say, okay, you singled out the segment. Well, if you look at the structure, there will be chunks where you have vertices from that segment, you have 0 vertices from that segment, and some chunks where certain vertices are present and certain vertices are absent. And then you want to analyze the edges that go across. So, you know, as I said, it's an inductive argument, so you assume you already have this bound. We have concrete constants there, so not just omega, there are concrete constants there. So if you put this into the inductive process, and then you say, okay, you now enlarge by one level, so you want to see how segments are distributed, and then you can make an argument by just counting. It's a counting argument. It's a little. So you kind of separate things into bad and good, right? And then count carefully what happens.
Asking what is the structure of the word set, the set with the smallest mass, because it should come out of the inductive proof.
The structure of the word set, let me remember. I seem to recall that the worst set is when you are actually not spread out too much across levels, but kind of more concentrated on the same level, but exactly in which parts I don't remember. So
The union of parts, the union of seven, the union of some.
something like that, yes, yes, yes. I have to, I mean, if you're curious, you can read our proof, and I will be happy to revisit the proof. You know, it's not off the top of my head, actually, what exactly happens in the worst case. But you can, basically we do some generous estimates and say, well, it's at least that, and at least this, and then we combine all of this, and then we get the 4 over 7 to the power, which corresponds to the number of levels. That's the important thing.
So presumably if you do this with the 8 to 4 of the trivial algorithm, you will get
Yeah, yeah,
the same by the same inductive.
yeah. It should give you the same idea, right? Except that the graphs are maybe less interesting than. Yeah. So that's the main lemma in a way, right? So the lemma says the expansion of decoding at level, you know, for k levels is given by this power of 4 sevens, 4 7 to the power k. And then, as I said, you specialize to the small scenario. So you say, I want to take this to be square root of m. You go like that. This is this. You rearrange the exponential and the log. And then you will see that this is the same as m to this funny power, where omega naught is exactly log base 2. So, yeah. And now if your graph is Strassen-like, so again, a recursive structure like this, but it doesn't have the particular look of 4 to 7. It looks like something else. You can make a more general argument that shows that still basically the same approach will give you this other magic omega to the power, well, 1/2, divide by 2 here, and then the whole thing will be like that. So this is for small, right, graphs. And so finally, how does this work? So then you get, this is the recap of what we already said before. So this is your expansion for small subgraphs. Now, you partition the whole graph, remember, into such subgraphs. So this is a restatement here. So the small set expansion for segments of size omega divided by 2 will be given to you by this formula. And then once you get this formula, you will sum contributions from all the segments to get n to the omega, right, times the quantity that you were seeing here. So that's the thing that you will get. So in general, what you see is that these are the arithmetic costs, right, times the expansion cost, or the expansion parameter for what? For a graph of size which is dictated by the local memory size. So that's what you will get. And so these are the input sizes, right, that can be accommodated by your memory. And the corresponding little arithmetic circuit will be determined by the arithmetic complexity, right? Because you'll get omega to the, m to the omega because of the arithmetic complexity. So you now see the ingredients. And then, as I said, this is at the kind of high level. So you have not gone very, very, very deep, because I didn't want to go into the 4/7 computation. But we can do that too. And the point is that this expansion for graphs of the size corresponding to these inputs, right, governs the whole communication complexity. So just a little recap. That's the same picture as we saw before, right? That's exactly this approach that is being implemented. And in terms of graph expansion, yeah?
The argument you used, I assume that you already had the ordering.
Yeah,
But the graph doesn't specify.
no. It's, you see, it's very generous. It just says you want to split it into segments, right? The only requirement we have is this, how you call it, pebbling requirement. That is, we want to respect the partial order on the vertices because we have it anyhow. Other than that, it's completely generous.
Any total order function
Yeah.
with this partial order, which
Yeah, yeah.
this way.
Absolutely, right. So it says for any split consistent with your graph, the following holds. Yeah. And one more thing, maybe, I thought I had this slide, or maybe not. Just a second. Whether these are actually good expanders. No, that's not what I wanted to say. These are not good expanders, so just a little remark on that. Oh, yeah. Yeah, it's good that they're not good expanders, correct?
That's the usual thing in
Yeah, so our goal is completely different. We don't want algorithms that are described by graphs that are good expanders, because that would be detrimental to minimizing communication, right? So if they're provably bad expanders, this is good for us. So we see kind of what's the worst thing that can happen, right? That's the worst thing that can happen. And you're correct, that there is a concrete worst case scenario you can actually look into. But this worst case scenario is still good in the sense that it's not a lot of expansion that's going on. Yeah, so that's the picture, right? That's the picture. We split everything, as you said, and this is quite general as to exactly how we can split it. Okay.
Is there a relationship between the kind of general expansion rate factor cheaters thing and the small set? I mean, are there any bounds that kind of relate them?
That's a very good question. So I think these are quite different problems, I believe, right? So small set expansion and global expansion, those are different problems.
Right. So it could be that you have some kind of a graph that sort of has, that if you somehow if m is the right size, its small rate expansion for whatever small set size appropriate is actually small. But when looked at kind of in a more global sense, it looks like, well, this is an expander graph. It's growing much too big. It grows much too quickly for the limit communications.
Is there any global to local results or local to global results about expansion? Can you say something globally if you see something locally on small sets? I think it's very tricky.
No, it's not cool. I mean, you cannot be
It's
expanding locally a small number.
right.
You cannot just, they're not expanders, they're
Uh-huh.
very high here. So
Yeah.
for why you expand
Yeah.
optimally.
Yeah. So these are not right. These, as you said, so these are not very much related. And so the beauty of what we do is that we don't care about what happens globally. But we care about small.
Right. So if you were to apply this kind of thinking, just say the fast Fourier transform.
Oh, that's totally fine. Yeah.
So I'm not quite sure how you would consider it, whether or not there's a lot of communication going on.
Well, if you,
But the memory size is sort of, I don't know.
oh, you can.
Big or small, you might get in fact really.
I think people are actually doing it right now. I know people who are interested in using this analysis for fast Fourier. And then you can just see what your graph is. And if it's nice recursive, like here, you can adapt these arguments. You know, maybe there will be more technical arguments. But you can adapt these arguments and see what small set expansion will give you in those cases. So it's very general. You know, it doesn't care that it's matrix multiplication, correct? It's just that it's very nice in the case of matrix multiplication, modulo this 4/7 to the k proof, which still needs technicalities. But the structure is very nice, right? And so if your graph has a nice recursive structure, then you can potentially run the same things and see, okay, can I do this? Can I do that?
The Fourier transform extraordinarily.
Absolutely. Yeah, yeah. So I imagine that, you know, and again, you can do maybe fancy Fourier transforms as well, you know, in groups that are not just, you know, simple cyclic groups. So, yeah, again, everybody is welcome to try that. I think somebody is looking into this. I have to remember. I should ask my co-authors. I think Jim would remember. And Oded has been doing a lot of implementation-related stuff, and Jim, of course, and some other people, including Benjamin Lipschutz and Gray Ballard. Gray Ballard is now at the Sandia Labs. So let me just show you one thing, and it's quick. Yeah, so this is the yeah. So this is the bounds again, and these bounds actually led to algorithms. So these all exist, and these are the algorithms that I showed to you on the first slides showing performance. So these were those new algorithms that we obtained. And just to finish it off, here's what Oded has. So Oded has this whole website dedicated to this stuff. So there are many, many more things there. In particular, some things where he was doing work with others, and of course Jim and Ben and everybody on. It's a big group of people interested in these questions. So there are very concrete implementation results there as well. A bunch of conference papers and a bunch of technical reports. So if you're interested in questions of implementing some of that, how exactly this works, what's the algorithm that does what, what's the scheduling you have to implement, people have been thinking about that. And up the hill there is the supercomputing center. This is run there. And there is Scale APAC group, LAPAC group all over the world, but especially its part in Berkeley, these guys are working. So basically, if there is a new advance, which is mathematical, they'll go and implement that. So we've been very, very lucky in this regard. Thank you.